the next speaker is Francesco De Anna, who will talk to us about linear instabilities of the Prandtl equations via the harmonic oscillator.
So, thank you very much. It is indeed a great pleasure for me to present this talk today. So today I would like to discuss about a recent result that I did in joint work with Joshua Kortum, a colleague of mine at the University of Würzburg. And this talk is going to be about boundary layers, and in particular the problem of linear instability of the Prandtl equations. So I don't know how much you are familiar with boundary layers, and therefore I would like first of all to give you a very brief overview of the theory and presenting the model, and also review some of the well-positedness results. Eventually we will see this is strictly related to the concept of structural assumptions of the fluid, which is the monotonicity assumptions and non-monotonic profile. Now, we will see in this talk that when we have the monotonicity, the Prandtl equations actually behaves very well. They are well posed in standard function space in fluid dynamics, whereas the real instability actually occurs when we lose this monotonicity. And for the sake of presenting our result, I would like to overview in particular a result of Gerard Varé and Dormy that was done in 2010, and it was about the instability of the linearized Prandtl equations in Sobolev spaces. Now, the way this result was proven is extremely important, since they built what I will call in this the next slide as unstable solutions, inflating quasi-eigenmodes. We will see very soon what does it mean. But the problem was that in order to generalize this to function spaces that were beyond Sobolev one would have needed a better qualitative understanding of this instability, up to understand how these solutions look like explicitly. And this is exactly what I would like to discuss today, our result. We were able, under specific assumptions on the perturbations we will consider on the shear flow, to determine an explicit formula of this unstable solution with tools that normally you will see in quantum mechanics, so via hypergeometric functions and algebraic eigenfunctions of the Schrödinger operator. So let us see this in details. So the motivations behind boundary layers, of course, is the understanding of viscous fluids when they have a very high Reynolds number and they are near a surface, as in this example. So basically, for the entirety of this talk, I will consider a two-dimensional fluid, and we know that the Navier-Stokes equations, together with no-slip boundary condition, under certain compatibility conditions of the surface, they are global in time, smooth, but the estimate associated to the viscosity, to the Reynolds number, the estimate associated to this regularity, they are not uniform with respect to the Reynolds number and the viscosity. And therefore, what's happening is that one can formally observe that when the viscosity goes to zero, one recovers the Euler equations, but the Euler equations require a less restrictive sort of boundary condition, the no penetrations boundary condition. So the flow is allowed to move freely on the tangential directions. And what's happening is a sort of concentrations phenomena where the dynamics become very often very close to the surface, turbulent and difficult to predict. Now, among the most important theory for the dynamics of boundary layers, there's of course the Prandtl theory, which is based on a particular asymptotic ansatz. The most important one is basically rescaling their normal directions with respect to the surface, what I've denoted here by the variable y, with these meaningful ratios of the Reynolds number. When doing so, and when considering also some further redefinitions of the velocity field, one starts observing in this region, in this limiting region, actually a sort of asymptotic equations, a leading order equations, and these are indeed the Prandtl equations, a form of which you can see on the right-hand side. So this is a sort of degenerate versions of the Navier-Stokes equations, and at a first glance they seem very appealing. And the reason is that, first of all, these equations are written only in terms of a scalar function. They are known as just a scalar function. It's the tangential component of the velocity field u. of the velocity field, whereas the second component V actually is implicitly determined by the incompressibility condition and the no-slip boundary conditions. Now, for the entirety of this talk, I will consider a very simple geometry where the tangential directions x is periodic and the normal directions to the surface is allowed to move freely on the positive line, so that the surface corresponds to y identically equal to 0. Now, another reason why the Prandtl equations are ideally interesting or appealing is the fact that there is no pressure anymore. The pressure is actually determined by the Euler equation, and in this form actually we assume it to be constants, therefore they're not appearing. And some viscous term is still present, so although it is not the Laplacian of the Navier-Stokes equation, we still have viscous term along the normal directions in y. Now, spoiler alert, although you will see that, say that this term actually is a good term, should the like provide regularization, actually is exactly the opposite. It's the coupling between the fact that we have a viscous term on the normal direction and this sort of non-linear, non-local implicit formula for V behaving like dxu. One has to know the entire values of the flow from 0 to y that will produce, in a general setting, actually unstable behavior of this model. And actually the nature of this instability can already be seen when linearizing the equations along what we call a shear flow, a profile, a velocity field of the form USY0 under appropriate assumptions on the velocity component USY. So let us see together a little bit of results in the literature about the existence of solutions. And as I was saying before, we need to consider two distinct cases. The first one is the case of monotonic profile, whereas the second one is monotonic. So this is something that you observe also in physics, actually. When you have a sort of monotonic behavior of the scalar functions u, so you consider it as a function with respect to the normal direction. You might have, for instance, the derivative is always positive or it is always negative. From a physical perspective, you still observe a sort of laminar direction. Therefore, there are no real instability appearing, and that this is also reflected by the existence of solutions of the Prandtl equations. Actually, from Olenek in '62, she were able to prove that in older regularity there exists local in time solution, a fact that was generalized later by Masmoudi in a Sobolev regularity through energy approach. The real problem actually comes when you do lose actually this monotonicity. So in physics, what you do see is actually if you have an adverse pressure, for instance, the flow actually accelerates much more quickly when it's approaching the solid, the surface, and therefore there is a first point of contact where this derivative is becoming equal to 0. And starting from this point, there is a sort of streamline where above the flow maintain a sort of laminar regularity, where below it starts actually inversing direction, and because of the viscous component on the normal direction, we start observing first turbulent behavior, difficult to predict. And this is really a problem about the viscous Prandtl equations. Actually, in the implicit Prandtl equation, also in this scenario, the system is well posed in Sobolev. But if you consider the viscous Prandtl equation, as I showed you before, in order to obtain well-posedness local in time, so just for a short time, one has to start beginning to control an infinite amount of derivative, at least in the tangential directions. And the first results on that was due by San Martino and Kaplish, and improved later on by Kukavica and Vikol, where they imposed a sort of analyticity along the tangential directions x. Now, this sort of analyticity is extremely natural if we do see that from the perspective of the linear equations around the shear flow. So, why so? Well, we can leverage the fact that we are tangentially on a periodic domain, and we can write the solutions u in terms of its Fourier decomposition. So you start introducing tangential frequency kappa, and solutions, quasi-eigenmode solutions that are these modes depending on kappa and are depending only on the variable t and the normal directions y. And then you project the linear equations along the quasi-eigenmode space. So in order to control the regularity formally of these solutions, one has to control how quickly these modes decay as kappa as the frequency progresses at infinity. Now the standard function spaces naturally are the Sobolev one, for which we impose sort of polynomial decay, Whereas the analytic regularity I was presenting before is actually imposing a very restrictive decay, which is of exponential type. So you are exponentially decay proportional to the absolute values of this frequency kappa. Now, how do you see immediately this sort of behavior in the projected equations? Well, you can naively think of this linearized equation as a perturbations of the heat equations, where the forcing term, the worst forcing term, is behaving proportionally to kappa times u kappa. Therefore, if naively you do some energy estimate and you try to apply Grunwald, in the worst case scenario, you will expect these exponential growths as kappa t. Of course, this will not appear, as we will see in the next slides, but this can be counteracted. This sort of exponential growth can be counteracted, imposing an equivalent decay of the initial data in order to ensure that this Fourier series actually is well defined and convergent. Now, the question was this just a purely mathematical technicality? So if I have Sobolev regularity for monotonic profile, and you can reach analytic regularity for non-monotonic, can we just improve the technique in such a way to approach the Sobolev regularity, understand at least function space that are in the between? And therefore, the community started analyzing for more than 20 years now, the so-called Gevrey class regularity, where we still have an infinite amount of control on the derivative of the initial profile in the non-monotonic setting, but this time is not so restrictive as it is for the analytic regularity. It is exponential kappa to the power of 1 over m. And the hope is that, okay, when m is equal to 1, we have analyticity. When m is increasing, we are getting weaker and weaker regularity, with the hope to get insights later on when m goes to infinity to Sobolev regularity. And there have been several results in Gevrey classes with respect to the Prandtl equations. The most important one actually was due by Girard-Varret and Dité, where they show that as long as you have Gevrey class 2 regularity, so if you impose the exact decay given by exponential minus sigma kappa to the power of 1 over 2, when you can prove that at least local in time, such a regularity can be propagated. And from these results, it seems that sort of the picture of the well-positedness of the Prandtl equation was completed somehow. And to understand that, we have to go backward in time. We have to go basically to the result I wanted to highlight from the beginning. It's the result of Dormy and Girard-Varret, where they show that the linear system around a shear flow which is non-monotonic, it is indeed ill-posed in Sobolev regularity, but they did so by building this sort of unstable modes, unstable solutions. So profiles u kappa that are not exact solutions of the Prandtl equations, but are very close, and they grow as with the ratio given by the Gevrey class 2, exponential sigma square root of kappa times t. Now, if you want to ensure that the Fourier series converge, then this will be a sort of optimal function space for the existence of solutions. Now, unfortunately, that's still not the case in terms of analysis. And this was done basically by us last year, together always with Joshua and Stefano Scrobonia. We proved that the fact that these modes were obtained through an approximations, that were actually sort of localizations of forced modes, the growing with this rate, we can ensure that they stick very close to an exact solutions of the Prandtl equations, just up to a meaningful lifespan, which is proportional to these values of the frequencies, logarithm of kappa, square root of kappa. And you immediately realize what is the problem, because if I'm hoping for my ill-positedness to have this sort of rate inflation, in the moment that I have at best this logarithm of kappa, square root of kappa, I'm going to lose this exponential rate to gain actually a polynomial rate increase that of course implies the Sobolev ill-positedness, but it doesn't give you any additional information for further function space. So we really are still far away from saying that the Gevrey class 2 is optimal. And now, in the next slide, I would like to convince you that actually this is not a sort of secondary problem. It's actually, if you really want to understand completely if this is really the optimal function space, the problem is posed beyond this Gevrey class 2, one has to take into account these localizations and this lifespan. And I'm going to do that with a very simple example. So we forget for a moment the Prandtl equations, and we consider actually something we are very familiar with, we know that it is well posed, which is basically a transported heat equations. And we consider it for simplicity in the whole line, in y can also be negative. Now we do know that it is well posed in Sobolev, but as we will see very soon, the way you build these unstable solutions for the Prandtl equations is trying to leverage the fact that you lose this monotonicity in a point. So it's more a local sort of analysis in a region where you want to build this sort of growing inflation. But you could do it naively also for this sort of equations that you know a priori shouldn't work. But let's have a look. So if I'm just interested, for instance, to produce a solution that is locally in a region, for instance, close to y equal to 0, have a sort of inflations in the frequencies, like here it's worst, is analytic sort of inflation, I can build an exact solutions of the problem. Of course, you understand immediately what the problem is, right? This is not with finite energy, right? It's growing in time, but it's also growing in space. But what I could do is actually saying, very good, I'm trying to localize it, perturb it in such a way that it is, for instance, multiplying it with a test function so that this is identically equal to 0 away with a local point, and hope that this inflation is preserved by the exact solution with respect to that profile. So what you can see below on the right is the dashed line corresponds to the exponential square root of kappa y coming from kappa equal to 1. And then you multiply by the test functions, and of course, because of the exact form within this region, this profile is inflating as time progresses. But now you go backward with respect to the exact solutions of the transported heat equations, and you observe that if you take the exact equal profile, because you know it is well posed, the solutions actually decay as time progresses, and therefore what you have is that immediate detachment of the perturbed solutions with respect to the exact solution. So this is actually a real problem. So for the Prandtl equation, it's not like that, in the sense that you can ensure that up to the time I have shown you before, it's proportional to that meaningful values in the frequencies, the two solutions sticks together, but nothing is precluding you that after such time, the viscous component of the Prandtl system becomes dominant, and therefore the solution starts decaying. Okay, having that in mind, let's go backward to the Prandtl system and see what was the idea behind determining precisely these unstable modes. And everything begins with a particular remark. So let's consider the linearized Prandtl equations with respect to the shear flow, and we assume that the shear flow is such that it's non-monotonic, so we have a point A in which the derivative is equal to 0, but non-degenerate. So the second derivative is different from 0. And what you can observe is that if you forget for a moment about the viscous term, you can write an exact solutions of your problem just in terms of the shear flow itself. So the idea in principle is the following one. You take your shear flow USY, you differentiate with respect to the values USA in such a way that in your point of contact, in your point A, this is becoming identically equal to 0. And then you impose it identically equal to 0 from 0 to A in such a way that your profile satisfy the boundary conditions at y equal to 0. And of course, you have a term, of course, which is rotating due to the fact that you have the transport component. But this profile in particular is an exact solutions of the Invicit Prandtl. Now, the idea is that you would like to have introduced now the viscous term and observe that this sort of attractor profile as kappa is increasing as the modes goes to infinity will provide a sort of inflation typical of the algebraic class 2 regularity. Because as you can observe from this profile, there is a major problem when introducing the viscosity back, is the fact that if you start deriving the first derivative with respect to u kappa has a jump. Therefore, if I'm deriving once more, you start observing a sort of singularity appearing, a Dirac, which is not allowed if you have like smoothing effect from the heat equation. And the idea of Dormier and Gerard-Varret was, okay, can I somehow produce an inner layer, so localize very close to the point of reversions of the flow, an inner layer that connect this attractor, so this the left-hand side of this attractor, this 0 value with the 1 value that will appear on the right-hand side. So can I do it in a smart way, a connections of this jump in such a way that in this particular region there will be a local profile that inflates exactly with the square root of kappa times t. Here I'm using their notations where instead of sigma positive, they have this tau. If you want the inflations, the tau has to have imaginary part negative. No? So that's in principle the idea behind that you want to do it formally. And how do you do that? Well, you start introducing rescaled variables. So you have your shear flow, which has losing its monotonicity in a certain point y equal to a, and then you introduce rescaled variable z, which are getting closer and closer to this point y equal to a as the frequencies increase. So region that are central more and more with respect to this point, and you rescale, of course, also you redefine as well your velocity field, your kappa, in terms of functions depending on this variable z. Here it's a little bit technical, but you should think in this way. Here you have the scaling factor I was showing you before of Gevrey class 2, and then the W represent the V component of the velocity field, whereas the derivative of W will be associated to the tangential component. As kappa goes to infinity, the Prandtl equations, at least locally, centralizing this point, eventually, if you want to determine this unstable quasi-eigenmode that inflate in time, eventually reduces to solve a very spectral condition, very special spectral condition, which is determine this complex number tau with imaginary part negative, so that this term will inflate as time progresses, and a W, which will correspond to the profile U, very, very close to the point, satisfying an ordinary differential equation. So you have basically the viscous term here, and you have basically the terms U. So this is an ODE depending on the parameter tau. So we really want to look about the coupling of the two. And of course, you want also to impose the boundary conditions at the minus infinity and plus infinity on one side 0 and 1, because you really want to connect the left-hand side with the right-hand side. And Gerard and Dormy, in 2010, then published in 2014, they proved that there exists indeed implicitly a couple eigenvalues, eigenfunctions of these spectral conditions. And finally, I'm in the condition to present the first implications of our result. This particular couple, eigenvalues, eigenfunctions, not only do exist, but can be written explicitly in terms of very simple parameter and very simple functions. And here is the result. So actually there exists a unique tau with imaginary part negative, and a unique profile W, and these are given by this very simple formulation. So tau is actually in the unitary circle, is minus 1 square root of 2, minus e square root of 2, so the imaginary part is negative. And V can be written in terms of exponential functions and the Gauss error function, so something that is very, very common. So you will say, well, this formula is sort of coming from the sky for the moment, but in the next slides, I would like to convince you that there is a natural way to derive it, actually, this particular formulation. But if you want to see if this corollary is true, well, what you do is that now you have W, now you have tau, you just plug it inside the equation and you see if this couple satisfy the ODE, and you let Mathematica do, so you just plug the values and you observe that this is indeed satisfying the identity. Much more important is that it is behaving as we were expecting. So you basically have that when z goes to minus infinity, is approaching 0, and is sort of approximating this Dirac. So as kappa will increase, it will become more inclined towards connecting the jump we were seeing before. Now the real question is, how were we able to derive such a model? And this actually is due to the fact that we were capable of writing any possible solutions of the spectral condition, making use of tools related to the hypergeometric functions. So hypergeometric functions are basically Kammer hypergeometric functions are actually solutions, the only entire solutions of this particular complex ordinary differential equations depending on two parameters beta and alpha. They are being used highly in optics, as well also for some problem in fluid dynamics related to turbulence, but that's the first time that actually has been used in order to obtain instability of the Prandtl system. For the sake of our results, to understand our result, what I would like for you to remember is just that these hypergeometric functions can be written very explicitly in terms of a power series. So you have a very similar form as an exponential power series, but with the contributions of what are known as Pochhammer symbol. It's extremely important to have this sort of explicit form because you do know how these hypergeometric functions are behaving at infinity for any values of the coefficients alpha and beta. And for almost any values, these are growing exponentially, except for some discrete values of alpha where the power series actually collapse to polynomials, since this Pochhammer symbol sort of generalize the factorial functions. So how can we use these hypergeometric functions to determine our solutions? Here, one of our major statements. Consider the ODE I showed you before with respect to a general parameter tau, and forget for a moment about the boundary condition. This is a third order ordinary differential equations, or you can see it as a second order differential equation with respect to the derivative of W. And you can write any possible solutions of the ODE as these very technical but explicit formulations in terms of coefficients depending on tau and hypergeometric functions of the first type. And among these, you can find the one you were looking for, actually, the one satisfying the spectral condition. Now, I would like just to, I don't ask you to remember the entire form, I just would like to bring up your attention to some aspects that are coming from this explicit formula. So the first terms is actually a good guy. You want to impose the boundary condition, right? Because you want to connect the jump. 0 at minus infinity and 1 at plus infinity. So you really want the derivative to go to 0, both at plus minus infinity. The problem is, so these terms, the exponential term, is actually a good guy because it's decaying as going to infinity, but as I said before, the hypergeometric functions as an exponential growth as for almost every values of the coefficients. And then you start, except for the values for which this collapse to polynomials. So you start observing that these are exactly given by a discrete values of tau. So you have a discrete amount of tau in which the derivative of the functions decay, and you can build your boundary conditions at plus minus infinity. And what it is interesting is that there is just only one value for which the imaginary part of this tau is negative, which means there is only one value of tau for which you can build an inflating solution. So you have discrete values of tau, they are all stable, they will decrease as time progresses, but basically you have one that it is, the one that I gave you before, for which actually time, as time progresses, the profile will grow in amplitude. Okay, but maybe you are still not convinced. How? So what I want to say now is this somehow related, this discrete amount of values of the parameter tau somehow reflect something similar you have in quantum mechanics as for the discretizations of the energy, you know, of respect to the Schrödinger operator. It's a huge jump, I know, but as we will see very soon, it's strictly connected to our problem, this. And to do so, let's have a look to the following further change of variables. So we go backward to the Prandtl equation, but this time I'm taking the simplest shear flow that is satisfying this reversion of the flow. So you have like the loss of monotonicity, but with a second derivative which is different with respect to 0. And what you can do, of course, is reusing the same scaling you had before. You have your y, your variable y, the normal direction. You have your critical point, and you define your variable z. Now, what you can do now is actually add an additional rotation, a manifold rotations to this change of variables. So you multiply z by this factor exponential minus pi8, so you rotate of p8. Why do you do so? Because when doing so, I can reformulate this Prandtl system in a form which is very, very close to the harmonic oscillator. So what you do basically is you write your velocity field with respect to this factor that should give you the amplitude multiplied by sigma and a string functions phi kappa. Now the phi kappa, when written with respect to the eta variable, so this rotated variable, is going to be denoted by the functions upsilon, whereas the sigma, under some further technical transformations, will become now the parameter mu. And under this transformation, the Prandtl equation reduced exactly, when we have this sharp flow, to the following ODE with respect to eta, which eventually you can observe is very, very close to the derivative of the harmonic oscillator. Now the Laplacian, the derivative of the Laplacian, will give us the third derivative of upsilon. Here I have a potential, a quadratic potential shifted with minus mu. When the derivative comes out, goes to the epsilon prime. The problem is that when I'm deriving the potential here, I will get plus 2 eta times upsilon. Therefore, I have a wrong sign. But still, what I can observe is that making use of this ansatz coupled with a particular commutator that I will show you in the next slides, I can write explicitly the solutions upsilon in terms of the solutions of the harmonic oscillator, so with one derivative less. So what you do basically is something similar to what was done before, always in the Prandtl system, which is reintroducing basically a new test function, a new function, sorry, a state variable, phi, which will give eventually your functions upsilon, your stream functions upsilon, making use of your operator, your Schrödinger operator. And you play with the equations, and a commutator, basically what you want to do is bringing the derivative inside the operator beta mu, and what you observe is some intrinsic cancellation, meaningful cancellation, that will reduce the Prandtl system along some technicality to a very important form. So if I'm denoting now phi prime by a function psi, so going backward, if I found psi, I have phi prime. If I have phi prime, I have a phi, and then I can find my stream function. The Prandtl system for the quadratic shear flow becomes a composition between the two operators of the Schrödinger operator, but shifted. So basically, your coefficient is not anymore mu, it's mu minus 2 and mu plus 2. And it's exactly this shift which produced the instability that we are gonna see, we have seen in the before. So by finding the kernel of one of these two operators, the most important one is the one where you shift to the right. So mu plus 2, so the mu will be shifted to the left actually. And you solve, what does it mean? What does it mean to solve, to find the kernel of this operator? It means finding the algebraic eigenfunctions of the harmonic oscillator, of the Schrödinger operator, solutions of the harmonic oscillator, but with respect to the coefficients mu plus 2, not anymore the functions, the eigenvalues of the Schrödinger operator itself. Now, the formula below is to say just that once you have the solutions in psi, you can go backward to determine the upsilon. And remark the following aspect, that we know how to write explicitly the solutions of the harmonic oscillator, or if you prefer, of the eigenfunctions, the algebraic eigenfunctions of the Schrödinger operator. These are written indeed in terms of hypergeometric functions and, of course, exponential functions. So you know that the energy is discretized, but it is always positive. But because now I have this shifting, I have this mu plus 2, I sort of shift the spectrum in such a way that the ground state now is not anymore 0, it's becoming negative. So I have one single values for which the energy is actually is negative and will generate indeed the instability. Now, if I'm looking to the related eigenfunctions with respect to these negative values of mu, I can find the eigenfunctions of the Schrödinger operator, and then I can derive through the formula I showed you before the upsilon. And as you can see, what is coming out is exactly the formula I present. It's very close to the formula I presented at the beginning of the W that was indeed inflating. So actually, this is the way you observe naturally this sort of instability. So what we did eventually, so this is the generalizations of the theorem. So the example I showed you before was for a very specific quadratic flow, but actually we can handle any family of quadratic shear flow alpha plus beta y minus a square when beta naturally is different from 0, so that the point is critical but non-degenerate. And if we do so, we can eventually write any possible solution of the linearized Prandtl equations in the form of a quasi-eigenmode, so growing as this exponential sigma square root of kappa t, explicitly making use of the upsilon functions I showed you before, how to derive in terms of these eigenfunctions of the Schrödinger operator. Now the real questions then to close is, can we then go further with respect to the lifespan I was introducing at the beginning? So are these unstable solutions that are holding after the time I was presenting before? And unfortunately, what we realize is that that's not the case. This sort of detachment actually in reality occurs. And here I give you an example of this case where you take the shear flow equal to minus y squared, and you get exactly the mu equal to -1 I was presenting you before, the unstable mode, which would correspond to the tau I introduced in the previous theorem. And the questions you have, can you build solutions of the form phi kappa prime y times these inflating values that are satisfying also the boundary condition? Well, the problem was locally you can do that, but can you connect it in such a way that you have an exact inflating solutions at any y? And that's actually not the case, because if you want for this exact unstable mode, impose the boundary conditions at y going to plus infinity, the profile you find now that is exact does not satisfy the boundary conditions at y equal to 0. Whereas if you impose the no-slip boundary condition, eventually the profile phi kappa is of exponential type, as I was showing you before. For any localizations, truncator will be dominant in the frequency as this kappa is increasing, and therefore there will be the detachment after such a time. This doesn't mean that they do not exist inflating solutions at any time. It simply means that they are not the one that have been found now, and further analysis has to be done. Just to conclude, I would like to make a comparison. So if you do remember at the beginning of this talk, there was this sort of attractor profile and the jump, and therefore the idea was to build a sort of way of connecting the lowest values at the left-hand side of the critical point with the highest value on the right-hand side. And Gerard Varian and Dormy, through the numerics, they generated that unstable profile. Here is written in terms of the variable z. But now, because of this explicit formulation that we do have through these hypergeometric functions, we can write explicitly these connections, what they call as a shear layer. It's really like an inner layer that connects the two, the jump. And as you can see, they do much precisely. So you have basically an equivalence of the plot. This is done by Mathematica, so it's really making use of the formula. This is done numerically. So with that, I'm very thankful for your attentions, and here are some reference about our results, and I'm happy to reply to your questions. So thank you very much.
Right. Other questions?
I have somehow questions and a bit of a speculation. So, okay, so make a big jump to liquid crystals.
Yeah.
And if you, say, consider shear flows, no, you're not too far from this, okay? Suppose even that you freeze the directed field, so then you're exactly this way. So, in active liquid crystals, as you know, the boundary conditions don't play much of a role at all in moving things. So you could have a flow like the profiles you showed, right? Say type of shear, but it's not driven by boundary, or it's not even driven by pressure. It's driven by, say, some internal activity, right? Like you know, some kind of biological, say, motor. So okay, my point is what. I don't know what you could say at this point, but what's your impression about, say, dealing with your type of analysis, but when you do not depend so much on boundary conditions, that is actually driven by some, say, internal force?
Yeah, so to certain degrees.
So you have a parameter, say that it gives you the amount of activity, and it's basically the amount of oxygen that you really put in the system.
So it's a very broad question somehow, but to certain degrees, this. So first of all, you know, this is a result of instability, right? So like the hope is not to get good behavior; it's actually the opposite, to get something inflating. And somehow, you know, if you start going away from this boundary condition, you are saying that you would like to go further away. You know, also for Navier-Stokes, it's well known that when you have the Navier sort of boundary condition, the problem is stable. Actually, you don't have like such a. You have this is related to the problem of vanishing viscosity limit. So you have a convergence of the Navier-Stokes equation towards the error. What I can say is for sure that as you introduce more complexity, you have actually the opposite of complicating the problem. This is well known.
For you, I think.
Say it again, sorry.
I think I'm simplifying it for you. Probably it's a little bit simpler. I think what you're doing. And in particular, there is.
Yes, but the question is: do you want to build unstable solutions, or do you want to show something coming at the limit that you can prove?
Well, it's various things. One of the things I would like to show is the transition, characterized transition to turbulence. In other words, go to worse behavior, which I see somehow through your stability analysis heading that way.
It will depend by the structure of the limiting.
Well, I can show you some equations later.
Yes, definitely.
So,
definitely
thank
definitely.
you.
Further questions? Maybe I can ask a question. So, how do these explicit solutions relate to these Gevrey regularity classes? I mean, can you?
Yeah.
So I don't know. I cannot directly see from your formulas where they.
Well, that's a good. The point, the Gevrey class, that's extremely important. Thanks for asking. The point is that all these implicit formulations, as you can see, they are written in terms of the variable y, right? I'm rescaling y to z, and eventually I'm producing this eta. So somehow the profile is just on the normal directions, where the Gevrey class regularity was on the tangential direction. So eventually, is this square root of kappa inflations that will tell you, well, Gevrey class 2 is optimal, right? Because the only way, if I have a sort of this family of profile that are inflating in this way, and when I'm saying they exist, they have to satisfy the boundary condition. I have to look them on the global plot of y in the normal direction. In the moment I want to ensure that the Fourier series converges, this profile has to be rescaled with a Gevrey class 2 sort of decay, but it's in the tangential direction, not in the variable y. What it does say, this result, is that we are still not there, in the sense that with the profile we have, we cannot build something satisfying the boundary conditions and going to zero at infinity. But again, once more, there is a limitations about this theorem, and in particular the fact that we can do exactly this only for quadratic shear flow, whereas there are, of course, much different one for which you can have different sort of form. Yeah, thanks.
Okay, if there are no further questions, then let's thank the speaker again. Thank you.